So let's start where we finished yesterday. So we've been discussing this idea of mapper, and let's briefly go through it. So the idea is as follows: we have a collection of points, which are sampled from something, and we may call this collection of points M. We have a function mapping this collection of points typically to the real line. Sometimes it happens that you are actually mapping to something a bit higher dimensional. So it may be one, on a few occasions two. And the main ingredient was that we are taking the range of f. So we are looking at the range of f of m, and we subdivide it into this collection of overlapping intervals. So the overlap is important. And then, well, we are looking at the clusters in the inverse image. And essentially, once we have the clusters in the inverse image, they correspond to vertices of our abstract graph. And if two clusters happen to have non-empty intersection, and this is very much possible, because again, you have those intersections of the cover element, then we put an edge. So that's mapper algorithm, and this is where we stopped yesterday. But before we go any further, I want to ask if you happen to have any questions about the stuff we discussed yesterday, maybe about this stuff. So if there are any questions, let's start with the question, and then I can take it over. Still got some sweets over here. I've got a little bit more in my backpack, so don't worry. We're still good. No questions so far? Okay, feel free to approach me during the coffee break if if you would like to discuss something privately. And let's go. So that's the mapper algorithm, and from an operational perspective, it does have a number of parameters that needs to be set. So let's actually summarize those parameters. So again, input is the finite sample from a manifold, and what we call the lens function. So that thing over here we call the lens function. And we cover the range of f. That thing with the overlapping boxes. We fix a clustering algorithm, and there's this relation. So let's look at the parameters. So we need to have the God-given lens function. We need to have the cover of f of m. The cover is typically given by two parameters if you look at the algorithms. So it's the number of intervals and the percentage of overlap. Question? Okay. And then we need to have a clustering algorithm with whatever parameters it's coming. So it's pretty often not to have a clustering algorithm that depends on some parameters. So there are also some parameters to be set over there. And the fact that we have so many knobs to turn is a blessing of the mapper algorithm, because it's very general tools. It's a curse of mapper algorithm for exactly the same reason. Let's take a look. So there's something you need to be aware of. So mapper gives us a structure, and then there is handy wavy. It should look like your initial cloud of points. And there is a lot of work in the community in trying to understand what does it precisely mean, under which conditions the mapper, if we are something more and more points IID from whatever manifold, when it does converge, and in which sense it does converge to a rep graph. So there is a lot of points, there is a lot of work over there. Point is, in a practical case, when a biologist is coming to you with a collection of points, it's very hard to verify the assumptions of the theorem. So it's, again, a leap of faith that you need to do, and when using it, and that's typical, but also something to be aware. So mapper gives us a structure. So we get the structure of the data. Of the whatever it is. There's this additional aspect. So on the top of mapper, we can actually plot some additional variable. And I always like to think about mapper as a way of plotting a function. So I have another function g from our manifold to real number. So that function may be plotted at the mapper graph. And what do I mean by that? So we have a function that have a value on m. Then what we can do, so if we go back, for instance, this cluster will correspond to a vertex in mapper graph. And this vertex covers a number of points. Each of those points have a value of our function g. So we can aggregate those values along the cluster. And for instance, typical aggregation is by computing an average value of a cluster. And then, well, since this is a real value function, we typically visualize it with appropriate color scale. Does this make sense? Okay, let's take a look at example, because it's always better to look at the example. And I think that this is one of my favorite examples. It's Monica Nicolau, Tom Levine, and Gunnar Carson, PNAS 2011 paper. So they looked at the NKI breast cancer data set. Yes?
There are some strategies to improve the F function. For example, this example that you showed, if we take the F to the horizontal axis,
yeah, you'll get something totally different.
Yeah.
Yes, that. Yeah, so it very much depends on the function, and function is a very much an element of the input, because it really tells you, okay, I don't care how thick this data set is in this direction, whether it's like this, or maybe it's like this. I don't care as long as it's connected how thick it is. So that's kind of a choice of the data, in this case thickness, that you are willing to give up in order to get a nice visualization of your data. How to make an educative choice? I would say what they say is to ask an expert. But it's a type of answer I don't know, so ask somebody else. So I was actually talking to the authors, every single one of them, of this paper. There is a lot of try and error. So you try and error, you get this, and I'll tell you what that is in a second. And then you say, okay, based on that part, I can draw some hypotheses. And then you apply standard statistics to try to verify this hypothesis. So, kind of the arbitrary choices you made allow you to observe something, then something needs to be verified. Okay, so let me tell you what the something is. So NKI is a breast cancer gene expression data set. So gene expressions for a few hundred patients with the breast cancer. The coloring is different, how much those genes are different from a healthy tissue. And NKI is Dutch Cancer Institute, very explored data set. Explored with various different tools. And what they did with Mapper, again, that's this Y-shaped thing. The interesting thing they realized was this part. So, it's roughly 20% of patients. So those patients, that's a very bad prognosis. So estrogen negative breast cancers, bad prognosis. But those, and that actually, they based on this observation, they set up the biomarkers. So the coloring is by how different the tissue is from normal. It's quite different, as you can see from the color scale. But if you color with another variable, which is, the history of the patients, if they survived or not after let's say, the 5 years horizon. you realize that all the patients over here survived. So it looks like genetically a well-defined subpopulation with 100% survival. So if you ever got a breast cancer, you really want to be in this region. It is characterized by certain activities of certain genes, so they were able to verify it, and they run a standard statistical survival analysis to realize, okay, that what we see is actually over there in the data. So that's the verification step. Yes. Okay. I'll throw it to you, and then I will tell you about the dimension. So first thing, so NKI is roughly 20,000 dimensional. They made initial variable selection and some sort of projections. I don't think it was PCA, but so something like this. So they ended up with roughly 1,500 dimensional data set, and based on this, they did the mapper. So that was the pre-processing. All right. Any further questions? Yes.
I think you need a way to guess the number of intervals that you need, because
Try and error.
if you have many critical points, you need to cover those critical points with no overlap.
Absolutely. Okay, grab it.
How do you do that?
Okay, keep in mind, what I will say right now, some people may not like. So topology is based on looking for counterexamples to some hypothesis. And we are building, very elaborated spaces of Poincare spheres, or maybe spaces with critical points, which are many critical points. You look at the real data, you don't see it. I mean, somebody yesterday asked me, hey, am I aware of any data set, real data set, where you have torsions? I mean, it's such a basic thing, right? In Z2 you don't have torsions. Well, what type of rubbish you have? I'm aware of one. Maybe, if you count the Klein bottle in the spaces of natural images, that makes it two. There are many more other data sets in which we don't see anything like that. I mean, you look at you're trying to compute cup products, for instance, Stirnrod squares. Elaborated tools to develop to distinguish some complicated spaces in topology. I don't see any practical use. I haven't seen. I'm not claiming that it doesn't exist. I'm saying that the data sets we are able to process, I haven't seen them. So yes, in principle, that may be a problem. Whether you ever encounter in your real life, I don't know. I did not, but it doesn't mean it doesn't exist. So it's a matter of practice. Of course, I mean, the whole reason why the AI and the ML is working is because the data sets out there are reasonably simple. That's the bottom line. Sorry to be negative. I hope I didn't offend anybody in the room or online. If I do apologize. All right. So, that was something nice and important. So let's see. Let's see how it works. Let's play with Mapper. So over here I have very artificial data set. It's typical. So I have Mapper concentric cycles. Where is this? There it is. It's a very typical data set consisting of just two concentric cycles, or some people call it a bullseye. We use the Kepler mapper, so I have it installed, so I don't need to. So those are the concentric cycles. And I'll take, this is just, a scatter plot, and I think I'll take as the clustering algorithm, so the projected data, I took the first coordinate, so you can see it right here. So I took the y coordinate as a as the length function. As the clustering algorithm, I'm using DBSCAN. This is a density-based clustering, but in some other notebooks, you'll have a selection, so you will be able to see, to feel what's happening when you choose something else. So it actually does something, and it produced a mapper. So those are two concentric circles. It's just they are plotted in pretty non-trivial way. I think you can see it right now, or maybe Let me just run it again. Nah. So there is, as you see, a random seed in the plotting procedure. So we have one cycle over there. Actually, it shouldn't overlap. It does overlap. So let me plot it again. Now I'll show you a better plotting subroutine. Yeah, right now you can see it. So this is the internal cycle, and that's the external cycle. And the plotting is just because, it's not a figure 8. If I plot it again, you will see that this is not a figure 8. So that's the basic plotting subroutine in Mapper. We don't see any coloration. We'll see it soon in another example. And yeah, as simple as it gets. Where is it? So that's the Mapper thing. Now the second example, the thing I should change is this data set is pretty old. So it's coming from the attempt to understand the prices of real estate in Boston area from roughly 1970s. And somebody asked me, well, okay, what is the, okay, so there are 13 characteristics of every property. Okay, we can go to the notebook and maybe briefly discuss it. And what you are trying to understand, there it is. What you are trying to understand is what is the distribution. So our function G in this case is the distribution of prices of the properties based on characteristics like, the number of square meters you get, number of bedrooms, how close you are to the subway, what's the crime rate, how close you are to utility stores, etc., etc. So that's type of stuff. So we are getting, we are loading the Boston property data sets. And of course, you may ask me the question, okay, what's the reasonable function, right? I cannot take the Y projection right now. And in this case, normally somebody asked me over there, I would ask an expert. I'm not a real estate expert. Because I'm not a real estate expert, well, what we actually did over here was to use the TSNE, which is dimension reduction technique. So there it is. There's TSNE. I can actually try to make it a little larger for you. So we are projecting to the first dimension using the diffusion embedding. It makes sense or not, I don't know, but we do see some structure. So let me actually run Mapper. And over here, if you play with it, you can actually comment, uncomment a number of different clustering algorithms from dbScan, k-means, mean shift, agglomerative, or spectral, and actually see how the structure depends on it. So I won't necessarily be doing it right now. Not necessarily we have time. So we are still in this notebook. We don't have the procedure to color, but we see that in those particular parameters, we get different clusters that are connected. So in one of the next examples, we'll actually go deeper into the clusters. We'll try to see how the prices are changing. We'll try to draw some conclusions based on comparing why those clusters are so distinct and why prices may vary so much. Let me see. Are we still transmitting? I think we are. Okay, good. So that's a practical exercise number 2. And I think I'll stop over here because as you see, there's a number of things that you need to decide upon without the real knowledge about this stuff. Why TSNE? Why not UMAP? Why not to take the second variable or the first variable as we did so far? So let me tell you about, actually I'm going to speak about 2 potential alternatives. We are working on a few more tools, which we call topological visualization tools, generalization mapper type algorithms, or however you want to call it. So there's not trivial to choose the lens functions, not trivial to choose the other parameters. Back in 2018, 2019, when I was designing the ball mapper, that was kind of my motivation to kind of try to depend to as few parameters as possible. Of course, you don't get a tool which is so much versatile as mapper, but you get a tool which is easier to use. And I call it a ball mapper, and that's my standard example that I'm showing. So Let's not do a pseudocode. Let's again take a look at the sample point cloud. And you know, if you think about mapper, all those steps of going through the lens function, cover of the range, pull back, and looking for the clusters is really in order to find an overlapping cover of your data set. So over here, I'm proposing an alternative way of finding an overlapping cover. It only requires, well, if you say, I can say one, if you are picky, I can say 2 parameters. One parameter is a distance. So the question is, if I'm here, what's the distance I consider my neighborhood, right? Maybe Jesus is in my neighborhood, maybe you are in my neighborhood, maybe you are a little bit too far, so you're not in my neighborhood. And that's, you know, kind of the distance I need. So that's the parameter I want. But also, you know, you may say, okay, it really depends how you measure distance, whether I'm taking Euclidean metric or maybe, you know, cosine similarity that influence, you know, the shape of balls or the shape of neighborhoods. But once we fix the metric and once we fix the epsilon, I can select an what we call the so given an epsilon, I can select a subset of points which I call the epsilon net, which I call a epsilon net. So it's a subset of points having the property that for every point then there exists an element of the subset which is not farther away than epsilon from that point. So I try to put elements of the epsilon net with the colored dots over here. So that property really translates to the statement that for every black point, there exists a colored dot not farther away than epsilon from this black point. Okay. So if I turn it around, it really means that every point from my initial collection X is in the ball of a radius epsilon centered in one of the colored points, one of the points from my epsilon net. And therefore, if I take the union of those balls, it covers my entire set X. So it is a cover. Some elements may have some overlaps. And what remains to do is exactly the same thing as we do with a standard mapper, is to take a one-dimensional nerve, which is this thing. And then the question is, of course, how do you select the epsilon net? So that's also something to be aware. So in that version of mapper, if you select the epsilon net, we are using the greedy algorithm. So you are going through the list of points and you are looking for the first one which is not covered. If you don't have anything in your cover, you are just looking at the first point in your data set. You put a ball around it. You check which points are in this ball. And then you are looking for the first point which is not covered. And if you find the first point which is not covered, you put a ball over there. And you progress. Of course, you know, the way the centers of the balls depends on the order you are looking at the points. That's something to be aware. So when you are experimenting with the ball mapper, if you see something, permute your data a few times, make sure that you actually see the signal, and also look at the different radii to make sure that that's the case. It's not totally untypical to have this handicap. We are about to actually present an alternative version of the similar technique that doesn't have this problem. But you know, this is something to be aware. Tell me. Not necessary. Great. So you can try to find something like a minimal thing by solving electrostatic problems. So imagine that the landmarks are, you know, positively charged, so they are repelling itself, and you can. But what we care about over here is we really want to have those intersections, because they tell us about, you know, how the structure is interconnected. If you have minimal cover, you may be missing some intersections. So intersections are not necessarily bad, and therefore, you know, solving this type of electrostatic problem, in principle, you can. Really, I don't think you should, because this is not what we are looking for. Okay? Any further questions? Yeah, let's make sure that they don't get diabetic, because, you know, there are too many sweets going in this direction. Tell me.
we can consider the stack of kindness with the mapper as an one skeleton of flat boxes.
Yeah.
Then conclude.
So let me reformulate your question and tell me if this is what you asked for. So you're asking, why do I stop on the one skeleton, right? Because I can look at the, maybe there are triple intersections. You see this triangle over here. There is a triple intersection. So why not to put a triangle, etc. Yes, you can. It's a sparse ribs construction if you do it, and or something like a sparse ribs. It's really not the landmark based witness complex, but it's something in this direction. Yes, in principle you can. Again, keep in mind, and I think Jesus Gonzalez has this question yesterday. Why not to take higher dimensional nerves? Well, the reason is that's a visualization tool. If you want to use it to compute persistent homology, yes, you can, but it will be a different tool for a different purpose. So if you want to use it for visualization, stay with graphs. If you want to use it as a sparsification, yeah, sure. Yes, you can. Okay, makes sense? Any other question? Yes?
So, did you say how to choose the landmarks or how to?
Yeah, so I give you a greedy algorithm. Grab it.
It feels very much like K-means.
It is conceptually close to K-means, although K-means is a hard clustering. But we'll get over there very soon. All right. It feels like K-means, but again, what I care is the intersections. The K-means not necessarily give you the intersections.
Yeah, you use like
You can. Yes, that's another option. But you kind of end up with the same problem. It's not unique. Depends on the initialization. Very much like over here. So yes, you can. Are you guaranteed to have? So there's another thing over here. So the balls have the same radii. So you have a path. You can have an estimate of. If you're looking at the intrinsic distance, what's the minimal length between those points and what's the maximal length? Because you're really crossing a number of balls of the same radii. With the K-means, you don't necessarily have the same. So in principle, you can, but some interpretation may be different. All right. Anybody else? All right. So who knows this? I mean, that's my standard question. So who knows the answer? Please be quiet. Okay? You know the answer. So don't say anything. Say? That's a blackmailing, right? Okay, you know the guy, right? So here's the exercise. Let's see if you listen carefully to me. So I want to construct a data set, and you can actually find it online. So you put your lucky cat, the sculpture. Sorry? No, you just put a lucky cat. Imagine this is a lucky cat, right? And you can actually have. Can you please give me the duck? Yes. Please bring. Can you keep it? How called it, right? So and there is a duck, and I'm taking a picture. It's going, the same distance around the duck or the lucky cat. Thank you, Jesus. Please bring it. No, put it back. I mean that's an element of an audience. And you see, you get a picture of a cat front facing. That's I think the right side of the cat. This is the back of the cat. That's the left side of the cat, and then you see it front face. So that's not really relevant, but we have low resolution grayscale images. What I'm going to do is for every of those images, I want to flatten it into a vector, right? So this is 128 times 128 is 16,384. When I flatten in row by row into a vector. So right now I have a number of pictures of the cat from different angles, and they are converted. Wait a second. That's better. And they are converted to points in this 16,000 something dimensional space. What I'm going to ask you, Can somebody predict the question that is coming? What I'm going to ask you.
What is the shape of that?
Exactly. What's the shape of this collection of points? And I paid out double candy for the answer. Think about it.
You compute the square of X Lucas.
Reconstruct what?
Rotation in the X C. For example, in the different.
So okay, imagine you're taking a picture of me, of this region, and I'm rotating. Right?
And rotate.
Yeah, this is exactly what I did. You call the camera and I rotate it and you take it. It's almost like, you know, the police thing. But we got all the spectrum. Do you have an answer? You're raising hand. No? I mean, take a risk. Oh my goodness. Who said circle? Why? Okay, you got the right answer, so you get one candy. Now you need to tell me one in order to get the second one. Guys, everybody else who raised the hands, come later to get those, all right? You want to tell me why?
It will be a close curve, right? Because at every point you are rotating a little bit, so it must be close.
Whoops, sorry. It must be close, right? Because we are coming to the same thing, right? And are we coming via something that looks similar? Well, okay, if you sample, if you are taking more and more pictures, selfie, then eventually it converges into something continuous. Yeah. So, I mean, when I'm rotating, you don't see the same image as you saw when I started until I actually make the whole loop, right? That's why you start from some point in this 16,000 something dimensional space. Eventually you come back, and because you never see the same image in the process, there is no self-intersection, and therefore there is a closed curve. Very good. I mean, you come later for the sweets, and I should open the last one, the last bag of the sweets. There it is. Okay. Yeah, you can, but if they don't change, I mean, essentially, no algorithm that you are going to work on that you can potentially apply on it what makes a difference if there's very no or low variation. Yeah, so you can reduce it a little bit. Sure, there are many things you can do. And I'm not saying that, you know, finding a shape of a space of pictures of a cat is something worth trying, although you never know. Yes.
At some point, you have a picture,
Uh-huh.
and then if you let's say right,
Uh-huh.
have the direct reflected.
That's correct. So it's, you know.
I don't know if those need to be
Yeah, I mean, yes, I mean, you can work out the parameterization. This is essentially what you are saying. So a map from a circle. Yes, of course you can do all of this. But there's one more question I have. You want another question? So if you run ball mapper on full data set, you'd get this. What do you think? What say you? Tell me.
Some point the rotation, once the case that we're looking,
Mhm.
giving more information about it.
Yeah.
Because, well, looking at the map of if you look for the sun, there's more information. If you were saying like a little bit, you got one and the other.
So there's more information in the front, in the back. What you can do in the tool, you can actually ask. So where is the front and where is the back in this picture? Behind. Up is front, and this is the back, right? So excuse me, but this is for illustrative purposes. I need to rotate quite a while in order to get a distance because there are not that many details, as many as in the front. This is precisely what happens, and that's exactly what you can get from the algorithm. All right? Make sense? Okay, you can go and play on the repository. So for didactic practice, let's do the same thing. So there's ball mapper somewhere, and there's ball mapper Boston property. Where is ball mapper? Oh, there it is. Basic circle. It's coming up. So if you don't have it, you can install, or if you installed what Greg told you to install, you're good. Over here, we are just generating a simple scatter plot. Let me just restart it and clear so that we don't get the spoilers. So we are just using standard sine cosine parametrization. Get that thing. Creating a ball mapper with epsilon equals to 1/4. Get this, and of course, we can play with the epsilon as you wish, using the standard Euclidean distance. So that this is for 1/2. If we set epsilon to 1, now we can still recover something. But that's it. You can also play with the metric, and we'll be playing with the metric in one of the examples that is coming. And let's look at the coloration. So in this case, I'm actually coloring the ball mapper with the time, and it's parameterized between 0 and 1. So now we start somewhere here, and no, it's not the. Wait a second. I'm using the variable y as the coloration. Okay. So this is where y is low. This is where y is high. So when you really look at this from a geometrical perspective, then the y-axis is going this way, and it's pointing this way. It's pointing to the floor. So this is where the y-axis is. Of course, topology doesn't care about the Cartesian system. That's precisely what we can see over here. And with the ball mapper, we have a number of fancy visualizations you can play with. So we'll be also playing with those. Maybe soon, maybe during the break. Let's see. The second one is, of course, the same Boston property data set. This time we will be able to see how the map on the top of the Boston property behaves. So let me bring it up. And again, I'm not going into the details of the notebooks. You have them in the materials. Feel free to play. Feel free to ask me questions. I'm here all the day today. I'm unfortunately not here later on, but you can always reach me via email. So if you have any questions, please don't hesitate. There's the Boston property. So now it's more or less the same business. So we are loading the Boston property data set. Those are the prices. And we are creating a ball mapper with epsilon equals 100. That's the coloration. So that's the ball mapper. Those are prices. So I think you need to multiply it by $1,000. So you can see how cheaply you can actually buy properties. The most expensive one are around no, you need to multiply it by 100,000, right? So the most expensive one was $250,000 back in days. What you can see is a cluster of properties which are relatively cheap, cluster of properties which are at least twice, maybe 3 times more expensive. And the question is, of course, which of the 13 variables that we looked at that actually are inputted. So one thing to understand, so the coloring function, the information about the price is not used to construct the ball mapper. So it is an additional variable. If you actually follow on the code, it's not used over there. So because we see this nice distribution of prices, what we can infer from it is that the variables we are looking at, they somehow influence the prices of the properties. And below, you can run some more analysis because there are only 13 of them. you can actually color by each of them, and very quickly you can realize what's the most discriminative factor of that tells apart those regions of cheap properties and more expensive properties. And over here you can also go through some more advanced analysis. So I won't be doing it over here. So the discriminative factor is in this particular data set is the crime rate, which wait a second, let me come back. Which is roughly 10 to 30 times, 10 to 20 times higher in the regions of cheaper properties compared to the region of most expensive properties. So this is what you are paying for, at least in that data. in those cases, you're paying for the safety. Again, you can play with analysis. I'm pretty sure that the whole statistical analysis can be made better, but it's very much like with the NKI breast cancer data set. You see the difference, you can draw a hypothesis, and then you can use all the possible tools to kind of verify it. And this is precisely what Mapper is about, or the ball mapper. It's for a tool to state hypothesis. And if we have time, we'll be able to come back to this in the context of pure mathematics. I'm not sure if we will have time. We'll see how it goes. All right? Any questions? Okay. All right. So I'm happily speaking about mappers, ball mappers, and stuff. Of course, we cannot ignore the fact that questions about visualization of high-dimensional data sets is something many people ask, because simply there is a need. Many data sets that people want to visualize, and of course we have competitors. So I named just a few of them, starting from standard linear dimension reductions in the directions of the largest variation of your data set, which you can get using principal component analysis or a PCA. And there is a group of nonlinear dimension reductions. Some of them care about preserving local neighborhood. Some of them are trying to recover the global structure of the data. Some of them are trying to do both to some extent. So you have, I just name a few, UMAP, TSNE, or FATE. All of them are coming with some theoretical guarantees. And of course, when you are trying to prove something, you need to usually put quite strong assumptions. In this case, the assumptions are that the data are sampled from some nice manifold. And there's one important factor which kind of tells apart TDA methods to those. So all of them are giving you an embedding of your data sets in whatever many dimensions you want. Typically for visualization, people choose 2 or 3 because this is what we can kind of deal with on the computer screen. For other means, you can do the intermediate projections, and we also may see the examples if we have time. But this fact, I mean, if you think about Mapper, and I'll have an example I think in the next slide. Mapper gives you a graph, and that's not exactly trying to embed your point cloud into lower dimensional space. There's a couple of advantages. One advantage is so Mapper and ball mapper, and one more algorithm that I'm going to discuss, they're also giving you some sort of data compression. So you may start with zillions of points, but if I'm able to find a nice cover of the ball mapper with 20 balls, what I'm visualizing with the ball mapper will be a graph with 20 vertices and maximum 20 choose 2 edges. If you are running those, you'll get an embedding of the zillion of points in R2. That's so you don't get this data compression. And that's one potential factor which may be useful. And there's another one, namely, not necessarily all the data sets are easily embeddable into Euclidean space. And let me show you one very simple example of a metric space that you cannot isometrically embed into Euclidean space of any dimension. So again, our competitors, the linear, the nonlinear, and nonlinear dimension reduction techniques, they are also trying to preserve the local or global distances. So here's the data set. It's a discrete metric space of 4 points. Let me call it A, B, C, and D. I'm not going to draw a distance matrix, but I'm going to draw a graph, right? So A is a distance 1 to all the other elements. So distance 1 to B, C, and D. And the distance from B to C is 2. That's the shortest path distance. From B to D is also 2. So A to any other is distance 1. And any other which is not A to any other which is not A is distance 2. Now that's a very nice discrete metric space of 4 elements, which doesn't admit the isometric embedding to R2 or any Rn, in fact. So the optimal embedding is exactly as you think. So if we put A as a barycenter of a triangle of the same sides, we put distance 1 over here. I think we get square root over there. That's the best you can do, but square root of 2 is not 2. And that's the kind of embedding with a minimal distortion. So when you are trying to force to embed your data into a Euclidean space, typically speaking, the data coming from biology not necessarily can maybe embeddable. So we actually have an example over here. So we have a definition of the isometric embedding, and we have this example of. So the thing on the left is another algorithm that we are actually should be appearing on arXiv right now, and we are submitting it. It's called the cluster graph. Coming back to your question about the clusters, let's talk a little bit about it. So what we did over here is we kind of sample more points. So we pretend that there are many more points which are very, very close to each other in all those vertices. We created a proper distance matrix. So the points from the vertex B, however many of them there are, they're very close to each other. Distance 1 to A, and distance 2 to all the points from D and C. Plus or minus something of the order of 10 to minus 9. So very, very small perturbation. So we tried to do the cluster graph, and I'll come back to this. We tried the UMAP, which kind of messes up totally the global structure. Tisny and Fati, they actually were very close to this minimal distortion embedding, but still, drawing the conclusions about the distances may be misleading. And over here in the cluster graph, we got a graph. This time it's coming with actually labels on the edges, and the labels tell you about the distances. So even though, if we look at this edge, it kind of looks very similar. Looking at the label, we know that the length is 2. So by actually having this graph data structure, we can get out a little bit of the problems we are encountering over here. Okay. So that may be a potential upper hand of the topological method. So let me briefly discuss this idea of a cluster graph. We have 11 minutes, roughly. So when you think about clusters, there are orders of hundreds of clustering algorithms, a few hundreds you can find. There's different implementations. That's extremely fascinating because question in how many different ways you can consistently partition some of the data set. We won't stop on the hundreds. There will be thousands or more. But when you are grouping together data into a clusters, you kind of don't know how the clusters are located with respect to each other. So here's a simple example. Of two data sets. If we look at them, I think, we could agree that there are 4 clusters in both of the cases. That's one observation, but the other observation is if we are looking globally at the geometry of how those clusters are positioned relatively to each other, those are different data sets. So if we run the clustering algorithm, we'll get an answer, okay, most probably there are 4 clusters, but we won't get an answer, okay, 4 clusters over here and 4 clusters over there, they are kind of, differently distributed. So what we did was something very simple. Let's assume that we are building a graph-based data structure on the top of whatever clustering you give me. And I want to assign the distances between clusters to this data structure. It's as simple as that. So formally speaking, we are taking a partition or a division of our point cloud X. We got a number of clusters, C1 to Cn, such that, altogether they are they're giving us the x. And right now, what we want to do is we want to lift whatever distance we have in our set x to the distance between clusters. So there are multiple ways you can do it. You can, there's my cluster and there's your cluster. We can look at average distance between our clusters, minimal, maximal, earth mover, and all those options are there available for you. And once we have it, we can just make a complete graph with edges between two clusters, and the label of the edge is the distance, the way we aggregate distance between clusters. So we aggregate distance between points of two clusters to get the global distance between two clusters. So this way we are getting a graph like this we have on the right hand side, which kind of give us an impression that okay, those clusters. So it's not yet a full graph. I removed some of the edges. I removed the longest edges right now. But if I remove the longest edges, what I can see is that that picture is stable for. So you even see the bar. So in one of the version of the software there is a bar you can actually slide, which tells you okay, I'm removing the edges of a certain length. So in that picture is quite stable. If you move it a bit sooner, then there won't be no edges at all. So we can see that there are stable regions for those graphs, which clearly discriminate those two clusters. We have an idea about the distance between clusters. Question? Makes sense, right? It's pretty. Okay. I need to concentrate to draw it properly. I'm sorry. You okay? All good. Okay, sorry. Yes. So imagine that we are looking at the points on my chart and points on the other chart. And for every point in my chart and for every point on your chart, there's, say, a Euclidean distance. What we can do is to take an average distance of all the points on my chart or all the points. You can take the minimal. You can take the maximal. You are making a choice. And once you make a choice, we average it and we get a distance between the clusters. Okay? Any other questions? Tell me.
The number of the line is the distance.
Yeah, that's a distance, right? So those are very concrete data set. I don't think the coordinates match. So that's something we can work on. Yeah, but those, yeah, it's the average distance. It's not the Hausdorff distance this time, so I need to actually check what's going on because there are fractions, and over here we have orders of tens. But in principle, yeah, you can use Hausdorff distance as well. Okay, no further questions. Okay, so we can go and play with various data sets. Over here, I don't think I'll be presenting the details. You can look at the preprint. Actually, it should be on archive today or on Monday, the latest. So this is some diabetic data set. This is some fake data set. So we constructed we had a little bit fun trying to find data sets which UMAP, Tisney, and Fate gives totally nonsensical answers, and we are getting good answers. The typical recipe is you take a data set which have relatively low intrinsic dimension, and you embed it into very high dimensional space. So the data set we have over here is we sample points from two perpendicular lines, but they don't touch each other. So those lines are like this. And in addition, somewhere far away we have points from Gaussian, sampled from a single or two large Gaussians. So roughly the number of points in every line and number of points in each Gaussians are more or less the same. And then we embed those things in, I think it was 500 dimensional, data set. PCA gets one of the lines and aligned with the Gaussians, UMAP, Tisney, and the Fate. And The cluster graph obviously recovers it for most of the clustering methods. So we got a lot of fun. We also played with different biological data sets because from our experience, the biologists we are collaborating with, they look at a Disney plot like this, and they're trying to infer that, which is totally wrong. So you should never do it. Disclaimer: never do it at home. Those two look close and they're far away from something else, and therefore, they're trying to make some inference. That's absolute nonsense, because if you change your random city in your Disney, you get very different layout, and all your conclusions go to the trash bin. So over there with the cluster graphs, there is some certain types of robustness. But there's another thing which I think is important that we did, because I'm standing over here behind you for almost 1 hour, waving my hands, saying that mapper has a similar shape that your initial point cloud, without being specific of what that means. And thankfully nobody asked, because I don't have a good answer to this. And I may say, okay, in a categorical way, it converges to a rep graph if you have sufficiently many of points. But it doesn't mean anything for your fixed point cloud. So let's try to actually put a measure, put something like, I really like to think about it as a p-value, but because we have a statistician in the room, I won't call it a p-value. But something as, how certain I am that the visualization is actually representing the underlying structure of my data. So I think it's in the next slide. So once again, we need to have some assumption. Let's assume that we are sampling our points from a manifold, and there is an intrinsic distance on this manifold. It's an intrinsic metric. What we can do, and there are a number of ways to estimate this intrinsic metric. So given 2 points on the manifold, there is a way, if they're actually on the manifold, we sample dense enough, there is a way to get an estimator which is consistent of intrinsic distance. So given 2 points for if I'm sampling from a torus, there is a way that if I have a sufficiently dense sample, I'm able to find an idea of how far away they are from each other intrinsically. So there are multiple ways. We chose the idea of building k-nearest neighbor graph. So I'm connecting every point to the k-nearest neighbors, and then I'm solving the shortest path problem on the obtained graph. That's a good estimator of the intrinsic distance. And right now, what I want to do is I want to build. I will say that my cluster graph or my mapper is good if it preserves these intrinsic distances that we are estimating. So what do I mean by that? I have a good picture. So let's see that I have this picture over here, which is this cross-end data set. I probably did what I did over here was to use k-means with k equals to order of 10 or 15. We see those different clusters. And when I do the intrinsic distance, and if I want to move from this point to that point, I'll need to go all the way, right? So, but if I do the full cluster graph, there will be an edge between this cluster and that cluster. So the way I'm lifting, so if I'm given 2 points from my data set, there are two options. Either they are in the same cluster, and in this case, I consider, okay, their distance is 0. Those methods also provide you a way of compressing your information. So those points are, from this perspective, indistinguishable. Okay. So, better that they would also better have the intrinsic distance, this k-nearest neighbor distance, small relatively to other distances on the data set. But if they are in the different cover elements, if they're in different clusters, then I can also solve the shortest path problem on my cluster graph. Well, I get the shortest path. So if I have a cluster graph like this, the shortest path is this one. It has a length of 1.59, and of course, if you go around, you are going much farther. So every single one of them is around 0.3. There are many more of them, right? So definitely the shortest path is over here. But then I realized that if I'm actually looking at the estimation of my intrinsic distance, that this thing is a shortcut. So I can define this metric distortion, which I have over here. So that's an average I'm taking points from two clusters, X from Ci and the Y from Cj. I'm computing this, the absolute value of the logarithm of metric distortion, and there is a good reason why for every of the component. And I'm taking the average between two clusters. And if this thing is large enough, I say, okay, there's too big distortion. This edge should not be there. So this thing gives me a way of pruning out the edges which are shortcuts, which don't represent the distances on the manifold. And at the end, I'm getting kind of cutting a little bit longer story shorter. I'm getting a nice data set with kind of minimal number of edges. So we have so first of all, it gives us a way to prune our cluster graph in order to get smaller number of edges, but also to if we are looking at the overall metric distortion, it tells us something about the quality, how good or how bad our cluster graph is, and that gives some information whether what we are looking at we should be looking or just try once more with maybe different parameters. So this is how we are trying in practice for a finite sample of a data set. Under the assumptions, reasonable or not, that those data are sampled from a manifold, maybe stratifold, that whatever representation I get in the form of graph with edges which are labeled by the distance preserves or does not preserve well the metric structure of our data. So let's see. What's the plan? We have a coffee break right now, and then 1 more hour. Wait, no. Because I may have a task for you for the coffee break. So we are not done yet. And there's another coffee break or not? No. Okay. So I want to keep you for 2 more minutes. All right. We will come back to tic-tac-toe later. We'll come back to music later. Oh, there it is. Okay. So I'll show you. You can also find those data sets that I'm going to present, but you can do one of experiment over here during the coffee break if you have your laptop. So that's a part of Warsaw I am living in. I don't give you my home address, but I walk around the block very close to my home, and I walk around the block with my laptop. And if you look at the folder, there is this thing called Wi-Fi loops, and there is this SSID experiment. So you may want to take a look at this. So I was walking, and there are a few houses. Essentially, every house there's an internet access with the Wi-Fi, and the Wi-Fi is characterized by SSID. So this is a unique identifier of every network, and I was registering those. You can find the data in the folder. But what is happening? I mean, I just draw a number of balls. They roughly, ideally, they should represent the range in which you can actually access a given. So, for instance, over here, whatever network it is, I can access it in this range. And I was registering when walking the strength of the network. And I make a loop. So if you think of the Lucky Cat example, that's exactly the same story, right? So I started over here. I heard a bunch of networks. And I moved a little bit. I'm not hearing them anymore, but I hear some new networks. Coming back, I hear the same networks again. That's colored by the time of my walk. Of course, that's not a coincidence. And then I tried figure 8. So I was actually moving around like this. That's city center of Warsaw. There are many more internet access points, and you also get the recordings. You get the file with all the data. And of course, I actually selected the parameters quite carefully in order to get those loops. Normally, you get a line, but then if you experiment a little bit, you change the radii, you can get something like this. And normally you get a hint because the coloration is the time of my walk. So how long in my walk did I reach to a given node? So over here, I think where is it? So I started somewhere here, and I went here, and there, and progressing on the color scale. I came back. One of the farthest point was over here, but then I came back. Keep in mind, those are average. So you get very high and very low number. This is something that we can also check from the implementation. Yesterday, I walked around the building, right here, this building. can try to reproduce it. So a few things. You can play with it. Immediately there's a ball mapper for visualization. Ball mapper both using the Euclidean distance and the cosine similarity. So yesterday the cosine similarity was mentioned in the terms of node to vector embedding. It's very useful over there, but it's also you can use it over here in this very example. It's not, I mean, you need to really massage the radii in order to see the cycle. So that's something. It always happens with the real data. I mean, theoretically, you should see the cycle. We can even prove the theorem. In practice, well, it's not that easy. Noise and stuff. So it's good to do this experiment to understand. But once you do the experiment, look at the coloration, and when you are changing, you can see which points are close. I don't have a cluster graph experiment with this. It may be nicer. So if you want to take a walk and see if you can reproduce it, grab your laptop and walk around the building. And tell me if you are successful. Other than that, let us have coffee. Thank you very much for your attention.